Okay, good morning. No, good afternoon. Let's start the class. So today we are going to talk about something I find it very interesting. So this is what is about today. So we are going to count the number of ways to put distinct items into boxes. Okay, but the boxes are not distinct. So let me give you an example. Items are distinct. So let's say we have two boxes, just simply two boxes. Box 1 and box 2. And then we have three objects, A, B, C. So how many ways can we put them into these two boxes such that both the boxes are going to be used? So in this, how many ways? How many ways are there? Let's do so we have three objects. Let's call it A, B, C. So we have A, we have B, we have C. So we have to use all of them, and then we have to use all of the boxes. So no box is empty. But then the boxes are not labeled. So how many ways are there to do so? Let's count. How many ways? Yeah, asking if it is. And brute force counting. You count it. So all the box has to be non-empty. All the objects has to be used. But then the boxes are not differentiable. So there are going to be how many ways? How many ways? Yeah, that's it. That's the answer. So how many ways? Three. Yes, there are going to be three ways, right? Now, notice that this is different from the case where the boxes are distinct. So if the boxes are distinct, then there can be six ways rather than three ways. And it is going to be different than the case where boxes can be empty. So if the box can be empty and the boxes are distinct, then there are going to be 8 ways, 2 to the power 3. But if boxes are required to be non-empty and they are distinguishable, then in that case there are six ways. But what we are going to find here is that boxes are now non-distinct. We cannot tell the difference between them. So what we are caring is about how the objects here are distributed or partitioned. And then this is the topic for today. It turns out that to analyze directly the number of ways to do so, it's not that. So there is a way to do so, we will see. But then a better way may be to start with the case where the boxes are distinct at the beginning. So we assume that these two boxes are different. So this is box 1 and box 2. And count the number of ways to put the items into the boxes. And after that, we get back the relationship between this one and this one, so that we know how to count this one. And then the latter problem, this red problem, is related to counting the number of surjections. So I will review what is meant by surjections, and then from which, all these problems are related to a number, a special kind of number called Stirling number. It's called Stirling number of the second kind. Okay? Okay, so let's see. So now we assume the boxes are distinct. So we now assume the boxes are distinct at this point. Are distinct. Okay. And let's have one more restriction, and has to be non-empty. Because in the end, we don't want to have any empty box in the non-distinct case. Okay, let's say the total number of boxes are, let's say there we have how many boxes? Let's say we have n boxes. Is that okay? And then how many objects? Let's say the number of objects is equal to, let's say we have R objects to distribute. Okay. And then, okay, and therefore, let's say R is greater than or equal to n. Okay. So we want to get a, we want to count the number of ways to distribute these R objects into these n boxes. Okay. And so far we have studied the generating function and the exponential generating function. Okay, so what shall we do? So is there a convenient way? So let's think about it. Suppose there are exactly R objects to put into the box. Is there a convenient way to represent a particular distribution of these R objects in terms of a string? So would it be a R digit string or would it be an n digit string? So for instance, boxes are distinct and non-empty. Let's say we are going to put A here and we are going to put B here. Is that okay? Let's say we are going to put C here. So this is one particular distribution. Is that okay? Is there a way to represent this distribution using a string? And if so, how long would the string be? So first of all, how long would the string be? Length 2 or length 3? Length 3. Okay? So we are going to represent this one because we have 3 things to specify. We need to specify A is in 1, B is in 1, and C is in 2. Am I correct? So probably we would want to have a 3-digit string. Okay. Now objects are distinct, so you can think of, let's fix a particular ordering of the objects at the beginning. So maybe we will always talk about A and then B and then C. Okay. So if we have this idea, then in that case, then we can represent this particular distribution of objects as the string 1, 1, 2. Is that okay? This specifies A is in 1, B is in 1, and C is in 2. Is that okay? So we can also specify a string something like 2, 1, 2. And what does it mean? Then it means A is in 2, B is in 1, and C is in 2. Is that okay? So we are going to have a R-digit string over an alphabet of size n. Is that okay? And then we want to count how many ways can we form a string of length R. Okay? Is that okay? Okay, there's a little bit restriction, but let's figure out whether we should be using generating function or exponential generating function. Which one shall we be using? Which one? Counting the number of strings formed by this 2, 1, 1, 1, 2, 1, right? Do we care about the ordering of the digits? Is 1, 1, 2 the same as 1, 2, 1 or 2, 1, 2? No, they are not. So even if we have the same combination of digits, we care about the ordering. So we should be using exponential generating function. Is that okay? Now, so we are going to have exponential generating function of what? Of what? So if you still remember, we should be having an exponential generating function that describes what is the requirement about this digit 1, what is the requirement about this digit 2, what is about the requirement of the digit n. Is that okay? So there are n types of characters that we can use. Okay, and then we need to specify the requirement. Okay, so we are going to have a EGF for 1, and then a EGF for 2, and then there will be a EGF for n. So when we have specified the EGF of them, then we multiply them together. So we combine them, multiply. So we multiply them together, we will get a EGF for our problem. So this is going to be an EGF for our problem. So that from this EGF, we can find out what is the coefficient of x to the power r. This is the idea. Once we find out the coefficient of x to the power r, we multiply it with r factorial, and this is going to be the number of ways to distribute r objects into n boxes. Is that okay? So if you are okay with this so far, could you please raise your hand? Okay, excellent. Okay, now the remaining thing is simple. Okay, what is EGF for 1? So what is the requirement about this digit? So we have many digits, right? So what is the requirement about how many ones can we choose? Recall that EGF talks about how many ones can we choose, right? So how many ones can we choose? Can we choose 0 ones? No, we cannot choose 0 ones, because in that case, box 1 will be empty. Can we choose 1 ones? Yes. 2 ones? Yes. 3 ones? Yes. Any number of ones? Okay. We can actually choose many ones. 1 million ones. Although r can be smaller than that, but that's okay. It won't appear in the term x to the power r. So in that sense, EGF is equal to what? We cannot choose 0 ones, but we can choose 1 1. And then we can choose 2 ones. And then we can choose 3 ones. And so on and so forth. Is that okay? And then this EGF turns out to be equal to what? Equal to e to the power x minus 1. Is that okay? Does that make sense? And then EGF1, EGF2, all of them are the same. So this EGF of our problem is equal to what? It's equal to e to the power x minus 1 to the power n. Is that okay? Okay? Good. Okay, now let's take a look of how this term looks like. Okay, so this is the EGF, and we want to find out what is the coefficient of x to the power r inside this term. Okay, so let's use what? Let's use binomial expansion. Okay, the binomial theorem. So we have e to the power x minus 1 to the power n. And then this is equal to binomial theorem, right? With summation of n is not n, let's call it r. R is equal to 0 up to n. N choose r. Is that okay? Minus 1 to the power r. This is, we choose, and then e to the power n minus r x. Is that okay? This is the binomial theorem, right? Double check. Okay. Yeah, yeah. So far so good, right? Okay. And then, so what should we do next? Okay, now we don't see an x here. X is here. So this is equal to what? Summation of r is equal to 0 up to n, and choose r minus 1 to the power r. And what is this? This is equal to what? This is equal to 1 plus 1 over 1 factorial n minus r x plus 1 over 2 factorial n minus r square x square plus, in general, 1 over. Let me reuse the symbol. So r is the one that we want to associate with x. So let me change the symbol a little bit. So sorry about this. So let's change it to j rather than r. Is that okay? So I want to change it a little bit. So this is j, and choose j. This is j, and then this is j, this is j, and then all of these are j. One over r factorial n minus j to the power r x to the power r. Is that okay? If you are okay with this so far, could you please raise your hand? Okay. So what is the coefficient of x to the power r? Do we know? So this is the answer that we want. Okay. So what is the coefficient of x to the power r? What is it? Let me see if I'm missing anything. So what is it? Yes? There. J. Thanks. Thank you. This is J. Thank you. Thank you. And this is J. Okay. So did I make a mistake here? So we now have, so this is the only term with x to the power r, am I correct? All the terms here doesn't have x to the power r. So we can get the coefficient of x to the power r fairly easily. It is going to be this term multiplied with this term. Is that okay? So this is going to be equal to summation of j is equal to 0 up to n, and choose j minus 1 to the power j, and then 1 over r factorial times n minus j to the power r. If you're okay with everything so far, could you please raise your hand? Okay, and so if I want to get coefficient of x to the power r multiply with r factorial, then I just multiply everything here on the right hand side with r factorial. So this 1 over r factorial will be gone. So this is it. Is that okay? So we get the answer. Let me copy the answer here. So the number of ways so this will imply the number of ways that we want is the coefficient of x to the power r times r factorial, and it is equal to a very strange term. This is equal to what? This is equal to the summation of j is equal to 0 up to n. Very strange, yeah. And choose j multiply with minus 1 to the power j multiply with n minus j to the power r. Okay? Very, very strange. Yeah, let's double check. Double check if it is correct. Is that okay? So checking. Let's check a more complicated example. Let's make this example larger. Let's say we have 4 items, 2 boxes. How many ways are there? So previously, how many ways? There are 3 ways. So here, I'm claiming that we should have 7 ways. Just imagine that we can distribute the objects. No, not 7 ways. Let me see. It should be, boxes are distinct, right? So there are going to be 14 ways. Any way of distributing the objects should be fine, except we put all the objects in box 1, and except we put all the objects in box 2. Am I correct? So there are going to be 2 to the power 4 ways to put the objects into the 2 boxes, and then minus 2 ways that we should not count. Is that okay? So in this case, when n is equal to 4, and then r is equal to 2, when r is equal to 4, let's check. When r is equal to 4, and let's say, so let's say when r is equal to 4 objects, n is equal to 2, then we should get the number of ways to be equal to 14. Let's double check with our formula. So let's double check with this formula. So in this case, we should be doing what? We will have 3 terms. So the first term is when n is 2, j is 0, 2 choose 0, times minus 1 to the power 0, is that okay? Times 2 to the power 4. Is that okay? This is the first term. And then the second term will be 2 choose 0, 2 choose 1, times minus 1 to the power 1, times 1 to the power 4. Is that okay? And then the last one is 2 choose 2 times minus 1 to the power 2 times 0 to the power 4. Is that okay? Is that okay? And then this term is 16. This term is minus 2. And this term is 0. So in the end, we get 14. Okay? Is that okay? Okay. Now this is a very strange thing, right? This is a very strange thing. How do we get an interpretation of this one? So this formula is really strange. Yeah, you have a summation of things. You have a binomial term here, and then this one fixes this part. It's not binomial term that we are changing the index here. We are fixing this part, and then the base here is changing, starting from n and then n minus 1 and then n minus 2 up to 0. Okay, so it is rather strange. Okay, now to interpret this.